All right, cool. So thanks for coming to my talk. I hope this can be a kind of fun exploration of some of the important algorithms and topics in physical prediction, inference, and design. So often this is going to be talking about partial differential equations, but it's a lot more general than that. And hopefully I'll stay away from most of the nitty-gritty details there. But it'll give you a picture of the kind of research that we do. And this talk is from algorithms to communities. And really, there's a lot more than just kind of working out the numerical analysis or getting a proof of concept up. And a lot of our modern science and engineering is really distributed team efforts, and community software is a really important part of that, and more broadly, communities of practice. And so towards the end of the talk, we'll kind of transition into more like what makes those kinds of communities work and how can we improve the practice of science, I would say.
Jed, I don't think you're sharing yet. It says Jed Brown has started sharing, but me and some others can't see it.
Oh, you don't have a screen?
It's just black screen.
That's surprising. It gives me a preview of my shared screen. It's odd because I do this like several times a day. I suppose you're still not seeing it, huh?
That's right.
Jed, it was working a few minutes ago before you started.
Still nothing?
Correct.
Are you sharing a specific window or are you sharing your desktop? Because maybe
I have it sharing a tab. I can try it here as sharing a window. I don't know if that helps any. We're still in the same boat. The preview that Zoom shows me shows that it's sharing. That's fun. Teo says it worked the first time I did it. The first time I did it.
Yes.
there we go.
Oh, it's working now?
Now
Yeah.
there's a slide.
Okay.
Try changing the slide.
Okay. I'll carry on. Let me know if anything else comes up. So where I guess I'd like to start here is kind of a big picture of how do different sorts of models use data and use mechanistic understanding. So this is like first principles physics or conservation principles or inductive biases. And so as you move to the right on this diagram, this means the state of practice relies heavily on data and the quality of the predictions, the quality of whatever the output of these kinds of systems are, they're heavily dependent on data, whereas going up, they're heavily dependent on mechanisms. And more or less, the bottom corner are problems that are really hard, where we don't understand mechanisms very well, but also we don't have very informative data. And when you look at this kind of figure, you'll see some here say climate, and you're like, well, why is climate over to the left? We've got lots of data. We've got countless petabytes of data. And the problem is we basically have one row of data. So we don't have a bunch of different Earths, we have one Earth. And the integral timescales for climate are somewhat comparable to the modern observational record. And so basically we have one row of data that is hundreds of petabytes wide. In other cases, maybe we don't have a whole lot of data, but we have the right kind of data. And so we can answer those questions really effectively. And so the physical in physical prediction, inference, and design is mostly sitting over here where we rely somehow kind of heavily on our physical knowledge. And often these are things like conservation principles, variational principles, say thermodynamic principles, and we try to use those, and often those give us something like in the PDE world we call a forward model. So that is, given a bunch of inputs, these might be initial conditions or boundary conditions, then we can predict what happens in the future. Now, a lot of these domains, say seismic tomography is an important one. The problem is we want to find the inputs to the model that agree with the outputs that we can measure. And in this case, there might be a lot of data. This is like seismograms from lots of different seismic stations, but there's actually no direct measurement of the thing that we want to predict. And so it's quite different from a, say, purely data-driven approach, because you have no outputs. All you have are a bunch of indirect measurements. And we really need a model to piece together what's going on. In the machine learning world, we tend to say we're using inductive biases. So each of these points, or each of these domains, as we use data more effectively, we can move to the right and get better predictions, more reliable systems, or we can use physical knowledge, which often means developing new knowledge or finding ways to apply our understanding to become more informative for that domain, and then they can move up. And the goal, of course, is we would like to have really reliable systems. In a lot of domains, that seems to be a bit hard to access. So I'll give you one example of a project where we've been doing this kind of thing. And this is a project called Cricket. It stands for the Constitutive Relation Inference Toolkit. And the setup here is we have some experimental configurations, and there are natural observations. So this could be experiments in a lab. It could be satellite measurements of the Earth. But nature is doing something. We have some kinds of observations that we can make of that natural system. And then we want to replicate that process in computation. And so we're going to develop models, and those models usually encode some principles, say, of conservation, and then often they have what are called constitutive relations. And these are much less constrained. They're functions that have to be what's called equivariant. And we'll get to that on the next slide, but they're functions, and they take in something like strain, which might be a symmetric 3x3 matrix, and they might produce things like stress. And there's lots of different kinds of constitutive relations. It's actually a big part of what happens at some groups at NIST. So if you go across the street over there and meet with some people, there's a lot of experiments, tabulation, fitting of those experimental data. But that's if you have pairs of the input and the output. And often in real systems, for interesting materials, we can't get those controlled experiments that isolate, say, individual materials, individual stress and strain pairs. And so instead, we want to take indirect measurements of some in situ system. For that, we need a PDE solver. And this might be simulating forward in time. It might be solving an equilibrium problem. Often it's going to require implicit solves. It requires discretizing over a mesh, perhaps. So there's a lot of technology that goes into PDE solvers, and I'll look at some of the structure that we exploit in those methods. Then there's some post-processing, synthetic observations. Ultimately, there's a loss function, And there's a lot of engineering that can go into having good quality loss functions that tell us what we really care about. Ultimately, there's a broad class of inference methods where we take gradient-based inference or sometimes probabilistic methods that try to look for low loss. And often they're gradient-based. We get a set of parameters and then we say, okay, well, we have a constituent relation now. We can go off and solve the problems that we want to solve where we don't have observations yet. Put them into a control system, et cetera. So an essential part of this is to create constituent relations that are equivariant. And this is maybe the essential mathematical part of Cricket. There's a tool, you can check it out. This is a library that basically facilitates the previous slide. So the concept here is we would like invariance over some group of transformations, and a common one are rotations or rotations and reflections. And so the idea there is we observe some kind of physical system. I should be able to move my coordinate system somewhere else, or even step my coordinate system on a train that's floating by, looking at a physical system, and I should make the same predictions. I should understand that it satisfies the same set of equations. And so if the thing I'm taking in is, say, a matrix, and I'm computing a scalar value, maybe an energy, then this concept of equivariance basically means I should be able to transform from one coordinate system to the other, observe that, and come back to my coordinate system. And we should be observing the same quantity. Then there's the concept of equivariance. This is if I have a function that takes in a matrix and produces a matrix. And these concepts generalize quite a bit. You can have any old basket of scalars and matrices, and that's what, and vectors, that's what Cricket automates. So it's a modeling tool. You can say, here I've got a whole bunch of inputs, I've got this collection of outputs, let's go find equivariant models. And it relies on what's called the Feynman-Pipkin representation, where we take the inputs, we compute a complete set of scalar invariants. And so for a 3x3 matrix, there are 3 of those. They could be the eigenvalues, but they can also be trace, determinant. Any set is okay. An active research topic currently is how we can find sets of invariants that are well conditioned, which basically means we can compute them reliably in floating point arithmetic, and we can put together this kind of bottom of this slide in a way that's numerically stable. But as far as representation is concerned, you can take any set of invariants and set of form invariants. These are matrices, but there's nothing learned here. These are just direct functions. It's part of your modeling ansatz. And then what we need is some arbitrary approximation here. This can be any kind of function approximation. And it just needs to map this set of invariants to a set of scalar responses. Those get put together on the output and we get a stress. And so this is pretty cool because it does 2 things. One, every equivariant function can be written in this way. So you choose a set of scalar invariants. These are the gammas, and form invariants. In principle, you can choose those independently, though there's often a natural pairing. But you choose that representation, and then as long as you have a sufficiently rich function approximation, and you can get this by, say, an arbitrary neural network, but there are lots of expressive classes of function approximation. you can represent all equivariant functions in this way. Moreover, if you flip things around and you say, I have a function that is written in this way, well, it's equivariant. And so that's pretty cool. It's a really important kind of modeling tool. Cricket basically brings that kind of modeling in so that we can use lots of other libraries whose specialty is function approximation, but doesn't have a good way to express these kinds of constraints. And this allows us to train with less data, create reliable constitutive models, and then use those in applications. So an example of an application is part of this PSAP Center. So PSAP stands for the Predictive Science Academic Alliance Program. And we have a new 5-year multidisciplinary simulation center here at CU. And this is kind of the one-slide overview of what's going on. So there are experimentalists on the team, a few universities involved. They do experiments at their labs and at Advanced Photon Source. There's a bunch of data that comes out of this, some processing on that, image segmentation and such. And what we're interested in doing is simulating bonded granular material. And so there are grain resolving simulation that some of which just kind of exists and a lot of which we're building. That kind of goes in the box here. They're pretty expensive models. The goal of the project is to be able to create these coarse scale models, and the class of coarse scale models are micromorphic, is the term of art for that class of models. These don't have to resolve all the individual grains. And so there's some interface between these expensive models that resolve all the individual grains and models that are supposed to make predictions of thermomechanical properties without needing to resolve the grains. Those can then be used as engineering design tools. So an example of the kind of experiment, this is the first year of the project, so things are greatly simplified, but it will have, say, a cylinder with a bunch of beads and epoxy, and these get crushed in the lab. We get measurements of stress and strain. And from that, we want to infer properties of these materials as a composite. And things are going to get a lot messier in the coming years because these aren't going to be spheres anymore. They're going to be these angular crystals with a really big size distribution. There will be little pores where the binder doesn't fill in completely. But we take these kinds of experiments, which have CT scans from before and after, and then we want to put together what were the materials in there. And now let's make predictions in more complicated settings where we can't create that simulation. And so there's a few different software packages that we use, and they have different capabilities. And one that kind of resolves all the interesting mechanics is called GeoSMPM. And it's very expensive. So this plot is a little bit hard to read. The x-axis here is the number of simulated milliseconds per wall clock hour. So the processes here are sometimes pretty fast. But we see over here, it's going to take 1,000 hours to simulate 1 millisecond. And this is actually quite a large amount of parallelism to do that. It's running on about 1,000 nodes. Then there's some commercial software here called Abacus. These two packages only resolve the particles. They don't work with the binder. So they treat the particles as discrete objects instead of taking a field-based discretization of them. And our work here are the two blue dots. These are using our software stack, some new methods, new representations of some of the data structures and algorithms that allow us to speed up quite a bit, say relative to Abacus, and they allow us to access long time scales. So some of the experiments that we're interested in are very slow. And if you use what are called explicit methods, and all of the methods here, all of these methods are explicit, which means in order to get to the next time step, we just apply some kind of closed form algorithm to what we have at the current time step. And the point out here, which allows us to resolve the all of the mechanics of the system, is implicit. And most of our work is focused on implicit methods. These can take much longer time steps because they don't have to resolve the elastic waves that propagate within these samples. And so we can look at the physical time scale, which for slow problems of like pressing and curing are, they take many minutes or hours even. And so we can take time steps that are relevant and still resolve the mechanics. And so this gets us into what are some of the constraints when we try to run these sort of simulations on large computers. And there's basically two essential dimensions to this. One is latency versus throughput. So if I have a simulation and most of my time is waiting on communication, and really I need to take a lot of steps in a small amount of time, it might be a very parallel job. It might be running on thousands of nodes, but there's, we're kind of up against the fundamental latencies of sending a message from one node to another, or computing the sum of values from all of the processes on a machine. And on the other end of things, you kind of load up memory and you have lots of local work, and you don't have to be too concerned with the network latency. You're more concerned with bandwidth and the ability to compute locally. And if we look at the benchmarks, there's basically two types of benchmarks that are widely used in high performance computing. And they're both over on this end of the scale. So they're not, in a sense, they're not difficult parallel problems because they have lots of local work to do. Now, the vertical dimension here is looking at tasks that are compute limited. So these, it's not about moving data, it's about doing typically floating point operations, at least for the benchmarks, or doing other things, could be integer logic, but things that are really using the cores. And this scales really well with new CPUs and GPUs. We get more capability faster here. Versus bandwidth limited, you're needing to move data around a lot. And so frequently this is because we have data structures that need to sit in RAM, and it's quite expensive to bring those data structures into the CPU to be able to do something with them. And if when we bring them in, we don't have all that much, say, floating point operations that need to be done, then we'll be paying for bandwidth mostly. And a lot of the applications that we work with are kind of in this corner, which is very difficult. We're like fighting against what physics wants to provide us and what new architectures provide us. But this is really important. So DOE created the ACME program, which is now E3SM. It's their exascale climate modeling initiative. It's a large project. It's over $20 million a year across all of the national labs and a lot of university partners. And they had one objective. So it was a 100-page proposal. I was at Argonne National Lab at the time. And there was a whole section on performance criteria, but really the one objective was simulated years per wall clock day. The reason for this comes from a policy timeline. So we want to be able to inform policy decisions, and the IPCC assessment report, which comes out typically every 6 years, is the kind of biggest way to influence policy. And the timeline for that involves creating new models, calibrating those models, working with lots of other scientists at other projects and countries to put together a suite of tests that everybody is going to run with their models, running those, analyzing data, publishing papers, all in time to write the report. And so if you work backwards from that, they need about 5 simulated years per wall clock day for it to be relevant. Now, I made a conjecture back there. No DOE facility is going to run faster than the one that was at the National Renewable Energy National Energy Research Supercomputing Center, NERSC. And so this has turned out to be true. So they've rewritten code, they've run the code entirely on GPUs, on different new architectures that have come out. But the Edison line here, which is the green line, is a remarkably solid performing architecture. And so basically no benefits to the bottom line of the project have come from architecture. They've made things cheaper, but they haven't made anything faster. And so this is really important. This contrast is quite fundamental. So a different project, this is from a Swiss group, they rewrote their whole climate simulation setup for GPUs, and they claimed a lot of success. But if you put it on a chart here where you say, basically this is the rate of work per node, so it's kind of a measure of efficiency or throughput of using the hardware. And the x-axis here is the execution time per time step. And for this, we can plot different resolution models. And the whole point of this paper was, hey, we're going to do this for a 1 kilometer resolution model. And so that gives you 2 challenges here. One, how long do you have to wait per time step in order to be able to run at that speed? And the other is, how big of a machine do you have to buy to be able to run it at that speed? And their new model, which is the blue curve here, did give significant benefits on cost. I would argue the orange points can actually improve a bit on cost, but it is true that modern GPUs do better at this. So they improve on cost, and you can always reach your goal by using more money, that is, buying a bigger machine. But more money doesn't ever move you to the left. That's a much more fundamental architectural issue. And it basically, the picture hasn't changed in 15 years. So latencies are flat. They've actually increased a little bit as GPU-based machines become more popular. So I'd like to turn now to the other big limitation, which was memory bandwidth. And we have kind of upended our solver stack in order to deal with this. So sparse matrices are really popular. They allow us to do things like algebraic multigrid, sparse direct solvers. I've been a developer and maintainer of PETSI for a long time, and it's one of the core things that this library does well, and lots of people love them because it separates the abstractions between people who are developing models and people who do the algebraic solvers. And if we look at architectures, what we've got here, this is the y-axis is measuring flops per byte. And so we're looking at architectures and we're saying, if we bring, say, one double precision value that's 8 bytes, if we bring that into a register, how many floating point operations do we have to do on it before we can bring in another. And really, this is if everything is streaming. So we're reading from data, say in a nice contiguous stream, and so we can max out the bandwidth of the architecture. And meanwhile, we have lots of data in registers, and so we can max out the floating point throughput. And current architectures are all around 10 flops per byte. If we use a sparse matrix data structure, we get to do about 1 flop for each 6 bytes that we bring in. And so on this plot, we're way down here. The ratio between these is our efficiency. And so we're looking at something like 2% efficiency. So basically, the floating point units on new machines are useless if you're doing iterative sparse linear algebra, which historically has been the only game in town for kind of solving general purpose problems. There's another factor here, which is we're interested in getting more accuracy. And when we discretize partial differential equations, there's a choice of the order of accuracy of the method. And if we use finite element methods and the right kind of libraries, and we've developed some of those libraries, then you get to choose this polynomial order of the element. And so it's a relatively easy choice. It has a lot of consequences to pre and post processing, but you can freely choose this. And if you use normal assembled matrices, then you're on these lines that rise. And this is a log scale. So the cost increases a lot as you increase the polynomial order. However, if you can use matrix-free representations, then you can get on these curves that decrease. So the cost per degree of freedom actually goes down. The left side of this plot is the one that really matters. So this is the bytes per degree of freedom. The right side is what almost all numerical analysis of the last 40 years has focused on, which is flops rather than bytes of memory traffic. And so our work here is kind of trying to upend this system and make it so that we can spend our time doing more efficient things. And so when we set up iterative solvers, we end up having to multiply by the matrix a lot. And that can go into, multigrid methods and smoothers, but we end up having to access this matrix a lot of different times. And on the right here, we can see the cost, or really the efficiency. The y-axis here is number of degrees of freedom per second. This is running on a modern GPU. The bottom line is if we assemble the matrix and use Q-sparse. The top line here is when we use our algorithms, which don't assemble the matrix, and instead they apply it using a different representation. It takes a lot less storage, and it runs a lot faster after the lowest order case. So for the lowest order case, yeah, you can assemble the matrix, and it's the kind of access the usual algorithms. Beyond that, we have to make this kind of disruptive change where we no longer have a matrix with entries. We have a function that applies that linear operation. And there are certain things we can do with that representation. And within this library, we've been building out that capability. So libseed, we say it's fast algebra for finite elements. And it allows applications and higher level libraries to call into libseed and at runtime select what kinds of algorithms do we want to use and on what kind of devices. And libseed makes it so that we can apply the operators fast, and we can also get these ingredients that are needed for preconditioning. And I'm not going to try to explain how modern preconditioners work, but suffice it to say, we need this combination of what are called Krylov methods, which need to apply the matrix and apply the preconditioner and do some dot products. And the preconditioner is an approximate inverse of the operator we want to solve with. So we're trying to solve with, trying to solve something like AX equals B, and A is a big matrix. Maybe it's 1 billion by 1 billion, and it's distributed over 1,000 GPUs. And so the vectors X and B are also of height 1 billion. And we have A as a function that we can apply fast using libseed. But we want some approximate inverse of A so that we can solve with it fast. And that's what preconditioning is all about. Libseed provides some ingredients for that. It's based on an algebraic decomposition where there are some parallel aspects that the calling library can deal with. And our job is basically, in libseed, it's meant to run within a node, but it's meant to be run as part of a more parallel computation. And so we can do lots of transformations in this kind of middle part, fusing and kind of being smart about various operations here. But there's a bit of the user code that needs to be defined of what happens at quadrature points. This is where we define the physics of the problem. And there's some interesting choices that go into making that efficient. So when solving PDEs, we often solve nonlinear problems. And so for the nonlinear problem, we're creating some f of u, and there's a quadrature function that goes in here. These are things that the user provides in order to define their problem, or some higher level library that's more domain specific. We're very general purpose. And then we need a Jacobian of that. And there's various ways to represent these. One active area of research is how we can better use automatic differentiation to represent these components, basically make it easier for users to set up new models, but still take advantage of structure. And right now, there's a lot of things that a domain expert can do in this representation that automatic differentiation tools don't know how to do. Ultimately, this produces nice vectorized code. If you're used to looking at assembly, you would look over here and you would see the PD for pack double. And this is representing, we're doing well vectorized instructions that are all on registers. And the code that the user writes is kind of easy compared to our competitor frameworks, I suppose, which tend to be more heavily templated and ultimately harder to debug and harder to bind from different languages. Now, how do we trust these models? Well, there's what are called refinement studies that can be done using the method of manufactured solutions. And so we create artificial analytic solutions that we can solve using our discretization and compare to those kind of reference solutions that have these rich structures. And so we get convergence tests, and we can see by the slope of these lines that it is matching the design order of the method. That often doesn't apply in reality. So in a lot of hard problems, there are singularities that make it so that we don't actually see the design order of accuracy, but often there's a big jump, especially between first order methods and second order methods. So all of these slopes are basically the same, but the higher order methods do have smaller error at the same number of degrees of freedom. And you've seen on earlier slides that higher order methods become cheaper per degree of freedom if you do it right They become more expensive per degree of freedom if you do it wrong. And the diagram over here is showing how on practical problems, this is an error versus cost diagram. The high order methods can get us in the bottom left here, while the low order methods like 1 and these are 2, and these are successively harder problems. We kind of go like this. As we go to successively harder problems, the higher order methods become more important. So in this library, we've built out Julia, Python, Rust bindings. It kind of allows people to use their favorite modeling environments. And kind of briefly checking out some of the performance. On the left here, I have time per iteration, and on the right, it's the problem size per compute node. Up is more efficient in both cases. And so we see our lowest order methods. This is running on a CPU. The lowest order methods are very inefficient. As we go to high order, they get more efficient. We can see that all of these kind of drop to 0 efficiency at a baseline latency, which turns out to be about 100 microseconds per iteration. And we can see that they all kind of drop in performance here. This is because we drop out of level 3 cache for an important kind of working set. If we compare that to the GPU case, on GPUs, the minimum time is quite a bit bigger. And so you need something that takes like 400 microseconds or so to make the GPU pay off. But the performance rises and it actually doesn't drop until you run out of GPU memory. And so these are, it has a different sweet spot in a sense. If you think back to that diagram earlier of the latency versus throughput, if you're not right up against the latency wall, then you're going to have a more efficient method using the GPU. If you are right up against the latency wall, then the GPUs actually don't help. And a lot of applications are in that situation. There's work that goes into making these asynchronous. So the top line here, or the whole top part of this plot, is the profile of what's happening on the GPU, and the bottom is what the CPU is doing. And so we see the CPU launches a bunch of these kernels, lots of things happen on the device, and they get back for occasional synchronizations that are related to dot products. The result of a global dot product that involves communication currently can't be delivered to GPU memory, though that's something that we're working with NVIDIA on. So we built some applications for this. One is looking at elasticity, and this is, well, it's a different kind of deformation, but if you remember earlier from the PSAP project, we had a bunch of those beads in epoxy. And so we've set up multigrid algorithms for working with this. We have ways of representing the Jacobian, and it turns out there's kind of interesting modeling choices that go back to how you formulate your continuum mechanics for making this kind of deformation or this kind of solver efficient. This is what's called a flame chart. It basically looks at the call stack as part of a profile. And we see there are several places here where that same function that applies the action of the Jacobian shows up. And so some of our work has been, how do we model that efficiently, choose kind of what representation, and then how can we take these most efficient representations? So in this case, this is the most efficient one. How can we make it so that automatic differentiation tools like Enzyme, which works with the LLVM, will be able to produce these efficient representations without a lot of manual human time? Another part of this is how do we make our multigrid methods coarsen really aggressively? And there's a class of techniques called local Fourier analysis, which basically transforms solving a fixed size problem, say on a grid, to you can have a relatively small amount of computation that you need to do to predict the performance on an infinite grid. And a lot of methods degrade in performance as you go to larger and larger problem sizes. If you have to solve those large problem sizes, say using parallel computers, it becomes really expensive to do parameter studies. And so local Fourier analysis is a technique that we've extended a bit in a couple of prior publications, and now this library. And this was part of Jeremy's thesis work. He just graduated from applied math PhD. So there's a class of techniques that have not previously been considered multigrid methods or studied using local Fourier analysis. And they're called BDDC methods, but it gives us an algebraic structure. And it turns out that they pair really nicely with these matrix-free formulations. And so it allows us to coarsen really rapidly and have less phases of communication. And so this is a way to improve the strong scaling. And I think it's a pretty interesting kind of connection between the math and like libraries for a specific analysis task that then informs us being able to write code that solves real world problems more efficiently. And so this brings us to the broader community software development. So all these kinds of topics we've been looking at before, they involve fairly deep software stacks. And there's a lot of libraries, there's a lot of attempt to separate the concerns and to make abstractions that are not too leaky. But some kinds of problems here, and multigrid is a great example, where it's basically necessary to solve large-scale science and engineering problems with implicit methods. And yet, it's not perfectly reliable. It's a tool that has a lot of kind of ways to tune it and ways where you actually have to do some research to solve new problems effectively, or even variants of old problems. So it can be kind of a finicky endeavor. And yet it's the only thing that scales as O of n and that parallelizes well. So all the other methods that you pick up scale quite a bit worse and with bad constants. And so they just prevent doing the kind of essential large scale simulations. And so if we look into those libraries, and we maintain some of them, there's a lot of process that goes into it. There's a bunch of continuous integration. There's metrics like code coverage. So when we develop a new feature, we submit a pull request or a merge request, and it runs in a lot of different configurations, say 60 different environments, 200,000 tests. We get a table here of how the code coverage might have changed. So like, did you add a feature that doesn't have a test? Well, that would be something that would save reviewer time to know that. So reviewers are often people who are very pressed for time. They'd like to be able to give rapid feedback, to be able to encourage new contributors, ensure the quality of the project. And so there's a lot of tooling that software projects have created that make this really work. We want to be able to have the reviewer time focus on these like creative or unique elements. And beyond that, we wrote a paper called "The Community is the Infrastructure." And basically, there are a lot of different kinds of stakeholders who contribute to open source software. And if we take a particular library like Petsy, over the last year or two, there's about 100 people who have contributed in some capacity, and maybe 20 of those are very active. But none of those people are funded to be like a full-time developer of Petsy. Instead, they're solving their own problems, and Petsy is the way to get there. And that's how I got involved with the project. I was a PhD student trying to simulate glaciers, and I found there were a bunch of algorithms that I wanted to use or I wanted to extend, and they weren't specific to glaciers. And so I wanted them to be available to other people. And so I started building components there and contributing and being active on the mailing list, helping other people out. And pretty soon I was like deeply involved in that community. And there's a lot of other people, but everybody's got their own responsibilities and their own milestones that they need to meet. And so we have to create an environment almost where we're tricking people into contributing to this common good as the way to get to their own goals. And it's a really interesting environment of how to like create that community that operates effectively. So with all of these things that we do for open source software, why don't we have continuous integration for research papers? Why is it that we like start a research paper from a new empty document? Why don't we start it from like a repository that has a bunch of tests where we can make an incremental change and all the data is curated right there, and it runs through continuous integration and we get a dashboard of how things have changed on lots of different metrics? Well, I would like science to look like that, but our world is incremental. And one part that I think is important and valuable is open journals, and in particular, Journal of Open Source Software and Journal of Open Source Education. I'm an associate editor for Journal of Open Source Software. And basically, there's a recognition that our open source software encapsulates a lot of knowledge, research level knowledge in many cases. It's the application of hundreds of research papers, but rarely do you take a research paper and just apply that algorithm out of the box. There tends to be more extensions and experience that you gain while using it in production, and abstractions change. And there's value to that, but it's not always value that goes into normal papers. And so Joss recognizes this and says, we should have a way to publish research software. And so Joss is a normal peer-reviewed journal. It has an open constructive review process, which takes place on GitHub. It's very developer friendly. It's not a huge amount of effort to write a Joss paper. The Joss review is not just of the paper. It extends to the repository. And so the basic review process looks maybe kind of normal, except in the middle part here. So instead of, say, having a paper and you write some line comments and you send it back, everything takes place on GitHub, and the review is of the software and the documentation of the software. And so reviewers actually install the software and they run tests. They can give all sorts of constructive feedback about like design of the software and maybe stakeholders who are not well represented in current interfaces, et cetera. But It is actually a review of the software and the documentation. The paper is kind of an advertisement, and usually the JOS papers are short, but the review extends to the whole thing. And so in many cases, the software may be 50 or 100,000 lines of code, or maybe it represents 20 years of contribution from a large active community. But it's a way to get academic credit, and we do it in a way that is very sustainable. So the total costs, none of the costs are borne by the author. These are covered from some donations, but our costs are less than $5 a paper. There's a bit of infrastructure that we maintain to make this operate. And JOS has been growing. There was a little pause essentially at the early in the pandemic when we didn't understand how to operate things, but it's been growing, more editors, more papers. As we wrap up here, I'd like to comment a little bit on how we distribute credit and the kind of the depth of this infrastructure. So this is from a wonderful report on from Nadia Egbal on this kind of depth of digital infrastructure and what stakeholders are perhaps overlooked in that process. GitHub has tried to communicate this, and so they created some of these badges. For example, this Mars rover or Mars helicopter badge. And this extends to lots of different software packages. Sorry, the bottom of this was meant to be hidden. So they had a list of qualifying repositories, and they took this list from NASA, and it kind of explored the dependency graph of the software that they had. And GitHub has other tools for kind of seeing this network, but it tends to be siloed by language. So it doesn't cross over. If you've written something in C or Fortran, and then you use it from Python, it doesn't get recognized in the same way. Moreover, SciPy is recognized, but there are no commits from Richard Bird or Bobby Schnabel, who are, Richard is retired from our department and Bobby is currently in our department. They developed some core numerical libraries that were, I think, written originally in Fortran and are embedded within SciPy, but there's no like commits with their name on it. And so if they have GitHub profiles, they don't get the contributor badge. So the other factor, there was a lot of simulation that happened before they sent up that helicopter. And a lot of that simulation was using a whole nother set of libraries that also didn't make this list because they weren't actually on the helicopter that was flying, but they were certainly necessary for that mission to succeed. And so I'd like to kind of wrap up there and hopefully take some questions. This is just a group photo from the spring where we had a barbecue. Yeah, thanks to the many sponsors who have made this possible. And I'm excited about ways to kind of better leverage our knowledge across the software stack, from intricate details of particular solvers to creating abstractions that people can really use, that use hardware effectively, library ecosystems that are effective to contribute, etc. Thanks. Go ahead and you can put questions in the chat or just speak or raise your hand, whatever you like.
I have a question.
Yeah.
So in the parallel least squares solver that's built into libc and PETC, how does the algorithm in a sort of pseudocode 10-second explanation break up that sparse matrix? And I ask because in terms of looking for other papers that compare that package to the more classic ways of doing least squares problems, I only found one that claims to be better than libc at all, and it does it because it says it does a different method of implementation for breaking that matrix up.
So I think this isn't actually a, mostly we don't solve least squares, we solve small least squares problems, but
yeah,
mostly, let's see. So there's, are you thinking of kind of this diagram?
Yeah, exactly.
Yeah, so here on GPUs, we have created a way to fuse all of this into one GPU kernel. On CPUs, the way that we do this involves reusing cache. And so basically we take batches of elements and we apply the restriction and then transformation on these kind of small batches that fit in level 1 or level 2 cache. The B operators here tend to be exploiting structure in a Kronecker decomposition. And so it's a bunch of tensor contractions. It's not actually a matrix. It could be represented as a matrix, but it would be much more expensive that way. But yeah, on GPUs, our fastest version uses runtime compilation to fuse this whole thing. The D here comes from the user. And that's part of why it needs to be runtime compilation.
Oh, okay. So D actually tells it how to space out the sparse matrix.
D tells it what the physics is. D can be linear or nonlinear, but it's implementing what the particular physical model is. Like, are we solving some form of elasticity, or are we solving fluid dynamics, or you know, and whatever else.
Okay, I think I get it.
I'd be happy to dive in more detail on that one offline.
Yeah, the question's a bit too nuanced for a talk, I guess.
Hi, Jed. I was just curious on the last little bit of the talk about the journal of open source software. Were you part of the team that designed this journal? Like, what was your role in the creation of this community?
I came on relatively early, so the first bits of process were set up. So I didn't create it initially, but some colleagues of mine were part of creating it, and as soon as the board started growing, they asked me to join. And so I've been involved since on a lot of different kinds of tuning the policies. So for example, one issue that comes up is sometimes you get authors who want to get a minimal publishable unit. And as the journal grows, there's more of those. And so we've always been kind of balancing, do we do a review on software that's not really ready, it's got too many rough edges, but the review can be instructive and we kind of lift people up and it becomes the sort of quality thing that lots of people will want to use for research? Or do we say that's just too much to ask reviewers to do, or maybe it just isn't that good a quality, or it's doesn't fit within its ecosystem that well, and then we'll reject it. And so our guidelines for that have evolved quite a bit. Say standards relating to testing. Be happy to give you lots more depth on dynamics of JOS if you're interested.
All right, thank you so much. All right, does anyone else have any a final question for Jed? Okay, if not, please join me in thanking our speaker. Thanks so much, Jed. Appreciate it.
Thanks a lot.